I don't have a joke for this one, so let's just get right into it. I've repurposed a seesaw to launch myself into the air. I stand on one side of the seesaw, and I have you drop a 1,500 kilogram mass on the other side in order to apply weight. What force does the mass apply to the seesaw? If my mass is 106.5 kilograms, what acceleration will I be launched with? And if the seesaw accelerates me for 0.1 seconds, what will be my velocity? So let's start by drawing out our variable list, and then let's actually draw out this problem. So this is both a kinematic and a forces problem, so let's make a variable list for both. So S, Xi, Vi, Vf, A, and T. And then F net. And in this problem, we've got two masses. We've got the mass of the block, and we have the mass of me. So we're gonna go M1, and M1 is gonna be the block, and M2 is gonna be the me. Okay, great. Now the other thing that we're gonna notice in just a few seconds, once we draw this out, is we're actually also gonna have two accelerations. So I'm gonna go ahead and make some room for that here. So we're gonna have A1, which is gonna be the acceleration for the block, A2, which will be the acceleration for the me. And let's go ahead and draw out our seesaw. It's gonna be just a nice little plank there with a fulcrum. And we've got a 1,500 kilogram mass. Then we have a Mr. Mincheski right there with a big smiley face because he's about to go for a ride. Okay, so let's take a look. Let's get our variables from the problem, throw them in. So 1,500 kilogram mass for M1, 1,500 kg, and then a 106.5 kg for our M2. Now, these are both scalar quantities. Mass is always going to be just a positive number because it's like time. You can't have negative mass. It doesn't make sense to have nothing and then have less of just nothing. Just like time. It doesn't make sense to be, we're at 0 seconds and now we moved backwards in time. That doesn't make sense. We can't move backwards in time. So what we do have is then a 0.1 seconds. And then we have an acceleration for the block. What is that acceleration? Well, if we do a quick little free body diagram, we see that the block is moving downwards according to the force of gravity. So it's going to have a weight that is the force going down, so it's going to be accelerating due to gravity. And let's define down as negative in this problem, and up as positive. So the direction that I'm launching is going to be a positive direction. So A1 is 9.8 meters per second squared. Great. Let's finish a free body diagram here. So it's going to, excuse me, it's going to fall towards the ground. It is moving, it is accelerating. So it really only has this force because the seesaw isn't really resisting it. Okay? If the seesaw was fully resisting it, if it had a force normal here, it would be in constant motion. It would have a constant velocity, or it wouldn't be moving. But since it is accelerating, it is applying a force to the seesaw. So now we could, if we were getting into really advanced stuff, we could calculate what my force is doing, resisting it, but we're going to just neglect that for this one. You guys don't need to worry about that. So then let's calculate the force, the F net, that's coming down. And according to Newton's third law, this is a third law problem, law of reaction, this force coming down here is going to be the same as the force coming up here. So F2 and F1 equals F2. Nice. Pretty. So let's calculate our force net. So our F net is equal to NA. So N for the block is 1,500 times 9.8. That's going to give us our F net. And that value is going to be 14,700. it's 14,700 newtons. F net is 14,700 newtons. So that is what force is the weight applied to the seesaw? Well, that's the force. That's our F net. So that's the first question we're asked. The second question we're asked is, if my mass is 106.5, what acceleration will I be launched with? So we're looking for A2. And hopefully I probably really haven't left myself enough room to write it, so we'll just erase that. So let's go ahead and calculate A2. So again, that's still going to be F net. That's going to be F net equals MA, because it's a reactionary force. It's my force that I'm being launched with is proportional to the force that this is falling down with. So F net equals MA, M2A really, and this would be M1A. So M2A2. So M2 is 106.5, and that's times A2 is equal to 14,700. Okay, so we can do that math really easily. See, this F equals MA on its own really isn't that complex. It's when we start getting a bunch of different forces acting on the same object, and we have to figure out which one is where. That's where it starts to get a little more complex. But just F equals MA, that's a pretty simple problem. So let's go ahead and calculate that. So 14,000 divided by 106.5. And that's going to be 138. 138. Yeah, 138 will be good. Equals A2. 138 meters per second squared. Excellent. Okay. So then we're tasked with finding the final velocity. What is the final velocity? If the seesaw launches me for 0.1 seconds, what is my velocity at that time? Well, we know that initial velocity is 0. Because before the block applies motion, I'm just going to be standing there. It'll just be, you know? Makes sense, right? So, final velocity is going to be given by Vf equals At plus Vi. Well, Vi is 0, so we'll just drop it. So Vf is just going to be At. Well, T is 0.1, and A is 138 times 0.1. Well, 0.1 just moves this decimal place 1 over, so I'm going to have a 13.8 meters per second for my final velocity. Excellent. Okay. That was pretty simple. Well, you know what? Let's take this one step further. What would be my height at the time that I leave the seesaw? Okay? So I'm leaving the seesaw at 13.8 meters. What is the height when I exceed the limits of the seesaw? You know, when it gets to this point, with the block here and me here starting to go in the upwards direction with that velocity. We can figure that height out. That's actually really easy. That's going to be given by S equals xi plus VIT plus 1/2 AT squared. Xi, 0, VIT, 0. So S equals 1/2 AT squared. We've done that problem 1,000 times already. So let's go ahead and plug in our values. So S is going to be equal to 1/2 times 138 0.1 squared. Let's go ahead and do that calculation. And that's going to give me a result of 0.69 meters. Beautiful. So not that bad. 0.69 meters. So that's about, that's a reasonable height. That's about this high, Or actually, even shorter. You probably more about table height here, maybe less. So now that we have that, what do you guys say we go all the way? Why don't we find the final height that I would reach? So I've launched off of this at 13.8 meters per second. Well, I'm gonna keep going. I'm gonna go until gravity decelerates me, and then I'm gonna plummet back to the Earth. So let's figure out my final height. So for that, we're gonna actually need to make a second variable list. Because this will be my initial value. My A2 will switch to a negative 9.8 meters, by the way. That should have been negative. So let's go ahead. S, Xi, Vi, Vf, A and T. I'm not going to need any forces here because the only force applying to me is the force of gravity, and that presents me with a constant acceleration. So acceleration is going to be negative 9.8 because it's a free fall problem, right? Meters per second squared. My initial velocity is going to be 13.8 meters per second. Well, at the top of my height, when I reach my final height, I'm going to have a velocity of 0, so 0 meters per second. So my xi is 0.69 meters because it's a two-part problem with the second part just being a continuation from the first part. My vi is 13.8 meters per second. My vf is going to be 0 meters per second because I'm reaching the top of my travel. When I reach my final height, I'm going to stop and turn around. I'm going to stop for a brief moment, and at that time, my velocity will be 0. So that's how I'm going to find this. So then I've got an acceleration. I'm going to need to find my time. So first we'll use the acceleration equation. So acceleration is equal to Vf minus Vi over t, the change in velocity over the time. So let's resolve that for time. So time, A and T are just going to switch places. Time is going to be Vf minus Vi over A, so we can plug those values in pretty easily. So T is going to equal 0 minus 13.8 over negative 9.8. And that's going to give me a nice healthy 1.4 seconds. It's equal to time. So then let's plug this 1.4 in, and we'll find our final S. We'll find my final height before I come crashing back down into the earth. So S equals xi plus vit plus 1/2 at squared. I have a value for all of these this time, so 0.69 for xi, vi is 13.8 times 1.4 plus a 1/2 negative 9.8, 1.4 squared. Whew, that one's a doozy. Let's go ahead and simplify that down. Okay, so once we simplify that down, we end up with 0.69 plus 19.32 plus 9.6. So let's add them all together and find out what our final position is. Our final position is 29.61 meters. Now that is actually a pretty high distance, 29.61 meters. I'd probably survive that fall back to the earth, but definitely gonna break an arm or a leg or at least a few ribs. So what's really nice about this little equation here is I've just been able to calculate a fun little game that I could play by myself. You know, set up a seesaw, get a car above it, drop the car, and see how far it throws me. Well, I'd get thrown around 30 meters into the air, and I'd have a really bad time after that point. Up until 30 meters, having a great time. Everything after that is a disaster. So I can do the physics on this little sport and figure out that I don't want to do it ahead of time. Thanks, guys. I'll see you later.